Hello, my name is Dylan, and today I'm going to be going over problem 5 from assignment 2, and this is also 6.25 from Streetman and Banerjee. Now, the question is right here, but I'm going to be going over it in the next slide, which is actually the summarized version. So basically, we're looking at an N-channel MOSFET. We want to lower the threshold voltage by 2 volts, and to do this, we're implanting a singly charged species at 50 kiloelectron volts of energy. Now the scan area is 200 centimeters squared. This corresponds to around 6.5 inches in diameter if it were a wafer. And the desired implant time is 20 seconds. Now we're asked for the species that we're going to be using, the energy, which is weird because we're given the energy, but we're still going to find it, the dose, and the beam current. We're also given the oxide thickness at 400 angstroms. So you might be able to remember this equation from assignment 1. If not, you should go study because it's probably going to be in the midterm. And well, we're going to be using this equation, or this formula, and we also have to remember that the silicon dioxide actually narrows the doping profile at the interface quite a bit when the implant goes through it, and also the problem actually describes the implant as a sheet of charge. So we can actually only look at the interface potential term in the threshold voltage equation and simply say that the change in charge leads to a change in threshold voltage, and the change in charge is due to an implant dose. So we can go and actually sub in all the values that we know, and we can find a implant dose of 1.07 times 10 to the 12 ions per centimeter squared. Now I lost a mark because of this in the assignment, and that is due to the implant actually taking part half in the silicon dioxide and half in the silicon. And because this is the case, we actually have to implant double the required dose, because half of it is going to go into the silicon dioxide, which means that we need 2.14 times 10 to the 12 ions per centimeter squared as a dose. With this, we can actually use the scan area and scan time to find the beam current. And the beam current, well, this is 3.45 microamps. Is it positive? Is it negative? Well, I'm just giving you the absolute value because we still don't know what species we're going to be putting into this semiconductor. So we can go further, and in a second we'll find the species required. So, and by a second I meant literally 1 second, because we'll find it in this slide. Well, we know that acceptors will actually increase the threshold voltage that device has because it's N-channel. So we want to implant it with a species that donates electrons. And where can we find a species that donates and is singly charged? In group 5. So if we look at group 5, we can see all these nice atoms that we can choose from, but the problem is, well, nitrogen we can't choose from because it's not as reactive and it has a low solubility in silicon. So we have to choose between phosphorus, arsenic, and antimony. Well, let's pause on that for a second and let's look for the implant energy first. Well, let's think about this. The implant energy in species actually determines the straggle and range of the species into the silicon dioxide and silicon, and the distribution is actually given by this equation down here at the bottom, where the ion concentration distribution is given by the dose per area that we found, the straggle, which is the standard deviation of this distribution Gaussian, and the projected range, so how deep it is of an implant on average. With this equation and getting these graphs from Streetman and Banerjee, we can actually put 40 nanometers, which is the depth of the silicon dioxide, and if we want it at the interface, we can find at 40 nanometers the energy required for each one of these species And from there, we can actually find the straggle at each one of these energies for each species. So we can tabulate everything and find that phosphorus is the one that we actually want as a species for 3 reasons. First of all, the distribution, so the straggle, is good enough compared to the others, the other species. We also know that the energy is minimized for phosphorus compared to the other ones, so we'll actually be using less power and saving money to the fab facility, and as well as the damage to the silicon dioxide is minimal because we are using the smallest ion out of the 3. Also, the implant dose or energy will be 30 kiloelectron volts because we actually chose phosphorus. So we hit 2 birds with one large stone here. So I went one step further and actually plotted the distribution and found the one for phosphorus, arsenic, and antimony. And I found out after finding the log plot that it was kind of a lie when the sheet of charge was described. Well, it shows a sheet of charge, and I actually plotted it 1-to-1 here. That's not the case. It's actually much wider than that. So we have to keep that in mind if we were to actually do this in real life. So thank you for watching, and hopefully you learned something new.